Hi everyone, this is Siddiq here. In this video, I will talk about uh, my recent work on self-supervised adversarial domain adaptation for improving cross-corpus and cross-language speech-emotion recognition. This paper is accepted in transactional affective computing. So these days, self-supervised learning techniques are widely being utilized in computer vision, in audio domain, and also in other NLP tasks. In contrast to these domains, we don't have very larger data sets in speech emotion recognition. So therefore, speech emotion recognition systems have poor generalization, and they are unable to perform well in cross-corpus and cross-language speech emotion recognition setting. So what we propose here, we propose an adversarial domain adaptation network. We call it ADDI. It's a dual discriminator network that utilizes adversarial learning to minimize the distance between source and target domain. That is called a domain adaptation. And we equip this model with self-supervised learning, and we call it SADI. The first network for the domain adaptation is ADDI, and the self-supervised version is SADI. So here is a brief comparison with the state-of-the-art research, and you can see in this table some studies in early 2010 and before 2017, they were using the feature normalization techniques to perform cross-corpus and cross-language speech emotion recognition. And then some people also explore by aggregating different dataset from different languages and see how it perform in cross-corpus and cross-language settings. And recently people start exploring the domain adaptation. Here you can see here, but the last column you can see none of the studies has utilized the self-supervised learning. So this is our one novelty. We have multiple novelities here, but I just want to briefly discuss here. So let's go to the network. So this is the network. It has three subfigure. So the second and third subfigure shows the second one shows the ADDI network, and the third figure shows the SADI network. The only difference you can see here is the encoder. This encoder is bold, and this encoder is not bold. This encoder doesn't have the bold line. What's the difference? If you see this dotted line is coming from the encoder here, it means this encoder is pre-trained for the SADI network, and here we randomly initialize the model. So what is the catch here? So we utilize self-supervised learning, as I previously mentioned, but we utilize in a clever way. So this is our pre-test task. We propose a pre-test task to generate emotional synthetic data. It means when we are pre-training the model using non-emotional speech, we are generating emotional synthetic data. So it means you are pre-training your encoder network, and as a byproduct you are generating emotionally synthetic data. That synthetic data you can utilize in your fine tuning to boost the performance. And this is the overall idea here. So I'm not going into the technical detail. I'm just briefly showing the results. So we utilize um, 1, 2, 3, 4, 5, 6 data sets. The library speech we utilize as the unlabeled speech for our pretext task to generate the synthetic data. So you can see here cross corpus, we have cross corpus results, we have cross language results, and we achieved considerable improvement using the SETI network when we are utilizing the self supervision. I just want to show the data augmentation. So here this table shows the use of synthetic data. So it means when you are pre-training, usually when you pre-train your model, you use the resources. But here the catch here, when you are pre-training your system, you are generating synthetic data, and that synthetic data you can utilize to augment your system. And you can see here you are improving the performance by augmenting your system with synthetic data. And then there is one more thing that I want to show you here. So in contrast with this 27th study, this is also on domain adaptation and it's recent study. So here I just want to show you here we are also minimizing the requirement of source level data. So here you can see here less than we utilize less than 85%, around 82% data, and we achieved similar performance compared to the state of the art study. So this is the overall architecture and the benefits of our proposed model. So here we perform multiple experiments, and this paper is available online, and you guys can have a look. If you have any confusion, any problem, you guys can send me an email and we can have a discussion. Thanks for watching. See you in the next video.